Well, thank you for coming to listen and to support Cure Alzheimer's Fund, who is an amazing foundation funding our research, and I serve as the chair of their research consortium. And I think if there's one thing to say about Cure Alzheimer's Fund, besides the fact that every dollar they take in is $1 out, they don't take any overhead out of donations because the founders cover all the overhead, is that the research that this foundation has funded over the last 10 years has really changed the face of Alzheimer's disease in terms of understanding, getting closer to drug discovery, and so I can't say enough good things about them. And I want to give you an overview of Alzheimer's, and my goal will be that by the end of my talk, that you'll know as much about Alzheimer's disease as anyone on the planet, and hopefully I'll leave you with some optimism that at least we know what we have to do to cure this disease. We have the knowledge. Our only bottleneck, our only constraint is getting public awareness and getting our government to fund this research and getting people to speak up for this disease. You know, I was speaking at the University of Rhode Island. I gave the commencement speech there a couple of weeks ago, and I told these new undergraduates who are graduating, new graduates, that their generation is being impacted by this disease more than any other because they are going to live, probably most of those kids are going to live till 85 years old or older. And at that age, it's 50% of the population, 50% that has this disease. So I said, so all of you need to know, thanks to modern medicine, you're going to grow old enough to have a 50% chance of having this disease. Hate to be, you know, a downer here, but you need to speak up for it because you have younger people speaking up for cancer and AIDS and autism, and that's great. And there are huge multi-billion-dollar budgets for these diseases, but Alzheimer's disease budget in the government is barely $500 million. 500 million, and if you really take how much of that really gets into labs doing, you know, the fundamental research, it's probably not more than a couple of $100 million. So it's a real issue, and there are so many great researchers out there. Cure Alzheimer's Fund supports them, but they're not getting enough federal support as leverage to get the job done, even though, as I'll show you, we very much know what we need to do. We just need the support, and we need people to speak up to get it done. So this is just some facts. You know, there are about 5 million victims in the US, 3.5 million deaths from Alzheimer's between 2000 and 2010, many, many millions of family members and unpaid caregivers. So the current cost of this disease in the US is $214 billion per year. So if you think about that, $214 billion in costs for care, and maybe, you know, 200 or 300 million for research from our federal government. So you know, for some reason, our government's been asleep at the wheel about getting this disease, getting the research for this disease increased. And then if you look worldwide, it's actually about 50 million, probably worldwide, that have Alzheimer's, maybe more. We'll have well over 100 million. I think that's a very low estimate, given how long people are living all over the world by 2040. So, you know, this is just, you know, this is a really scary figure that $214 billion for Alzheimer's alone. The total Medicare Medicaid budget is $861 billion. This says the research budget is $600 million all told, but again, a lot of that goes to big ticket items. They don't go directly to labs. But as you have 74 million baby boomers headed toward risk age, then you're going to slowly creep up and suck up most of Medicare and Medicaid's budget just with Alzheimer's alone. So it's a big, it's a major threat as an epidemic to our healthcare system. But as a disease, it's just a terrible disease. And just want to ask first, how many of you in the audience here have some direct interaction with an Alzheimer's patient, friend, family, or otherwise? Raise your hand. Yeah, so quite a bit. And so you know that this disease is terrible because you spend your whole life learning things and having experiences, making choices, creating memories with your friends, with your family, and your neural network in your brain, 100 billion neurons and up to a quadrillion connections, are basically taking care of all that information. And I just want to go to a slide while I say this, if I can go ahead for a minute. So you have 100 billion neurons, hundreds of trillions of synapses that allow you to have access to all of these experiences and memories that make you who you are. I like to say, like I said to these kids at graduation, The most important thing you do every day is make choices, because your choices create your experiences, and your experiences create who you are. Alzheimer's comes in and just basically robs you of all that because it hits this region of the brain. This isn't a mouse, but this is sorry. You can do this. Is that going yet? No. It's a new Mac, and every time they make a new Mac, they somehow screw up being able to do things. It's this tactile keyboard, and it won't let me hit the play button. There it is. So this is the hippocampus. This is the short-term memory area of the brain in a mouse with new methods where you can actually see within it. You see all these little bodies, these green bodies of nerve cells, and those wiry things are all the connections. So it's a very intricate, this is just in the mouse, and the human is even more intricate. And we're going to go into the hippocampus. This is where all your short-term memory and learning ability is. As you're listening to me, you may remember what I said 5 seconds ago because it's being stored in this area of the brain. And what Alzheimer's does is it comes in and it just insidiously destroys this entire neural network so that little by little you're unable to recall your experiences, your memories, or recall who you are. So this disease robs you and your loved ones of your own self. And it's really nothing worse than that if you really think about it. So let me go back a minute and tell you a little bit about the lack of budget one more time for Alzheimer's. And this panel up here shows that all of these diseases, AIDS, pneumonia, stroke, heart disease, diabetes, cancer, all had reduced mortality rates between 2000 and 2010. Only Alzheimer's went up 60%. We have never seen an Alzheimer's disease survivor. And then look at the funding for cancer, heart disease, AIDS during that period, and look at Alzheimer's. There's a correlation between how much funding for a disease there is and how well we do in reducing its mortality rate and reducing its incidence. So Cure Alzheimer's Fund was started by a number of founding families, and the idea was to put together a foundation where we go out and fund the best research, not waiting for it to come to us. So we go out and bring in the best researchers in the world. If there's a hot news story we hear about somewhere, we go out and say, we want to fund you. It's a very proactive approach. It's called venture philanthropy. There's no profit involved. It's nonprofit. Just like a good venture capital firm wouldn't wait for Google or Facebook, or LinkedIn to come to them, they go out and say, that's what we do. We find the best researchers, the best studies going on, and say, we want in. We want to help you push this faster and make your research go have higher impact. So this is the research consortium we put together. These are all top-notch individuals, including Nobel Prize winners, really the most celebrated Alzheimer researchers, genomicists, neuroscientists in the world today. And our basic roadmap is we start with genes, because most of what we know about Alzheimer's disease has come from studying the genes that cause this disease. And sometimes you read in the press misinformation that says, well, a little tiny part of Alzheimer's is genetic and the rest of it isn't. It's not true. There's a small percent of cases that are familial, meaning that you see a patient who has 2 or more first-degree relatives with the disease. And that's called familial. And often that's early onset because people might die of other causes, so it's harder to see familial disease in late onset cases. But if you look at the genes involved, and you look at the risk factors for genetics, whether it's early or late onset Alzheimer's, the common form, the rare form, genetics plays a role in virtually every single case. And I'm going to show you a large number of genes that are involved, starting with the first ones. But the key is we learn from those genes. If you want to fix something, you have to know it's broken. Genes can contain mutations or variations that either cause the disease or increase your risk. We learn from those genes what's going wrong in the disease. Then based on those genes, we do what's called translational research on how to fix them, bring that to drug discovery, and then finally to drug development. And in some cases, it's not drugs at all. In some cases, it's just lifestyle changes that can also work. So I want to cover a little bit of that at the end, too. So what is Alzheimer's? It's the most common form of dementia in the elderly. So people ask me all the time, my husband was diagnosed with dementia. Is that different from Alzheimer's? Well, dementia is the global term for catastrophic loss of cognitive ability, learning, and memory. Alzheimer's disease is the most common reason for that in the elderly. 90% of cases of dementia in the elderly are Alzheimer's when you do autopsy confirmation. I already said that. Now here's the thing. At 40 years old, approximately 40 years old and on, we all, except for maybe a few lucky genetic mutants here and there, they're still our cousins here at the Global Reunion, all of us start getting Alzheimer's pathology at 40 years old. And I'm going to show you what the pathology is. So as a geneticist, when I study this disease, I know that in just about everybody, this pathology is beginning around middle age. And the question I ask is, based on how you're living your life, based on the genomes you've inherited from your parents, even based on how your genes are being modified with your lifestyle exposures, your exercise, your diet, your stress level, the question is, when are you going to get Alzheimer's, not whether. So this is a scary thing to say, but I think if all of us live till 120 years old right now, given the numbers, probably all of us would at least be in the early stages of this disease. So you could say it happens as we get older, but the question is, based on genetics and lifestyle, why do some people get it as early as 20 years old? We have families where they get it in their 20s. Why do most people get it in their 80s? Why do we have so many families 50s, 60s, 70s? What determines that? How do genes and lifestyle combine to do that? Risk factors for the disease, age, number one, of course. The older you are, the more likely you are to get it. I already mentioned this, that over 50% of over 85 have this disease. Current lifespan is already 80. Just start doing the math with so many baby boomers on their way to this risk age. Family history is number two. Gender, women get it more than men. Even when you account for women living longer than men, and you correct for that, women are more susceptible to this disease. And now we're beginning to learn that there's one important part of this disease I'll talk about called inflammation, where the brain undergoes neuroinflammation. And women, it turns out, based on multiple sclerosis studies, are more prone to be susceptible to inflammation than are men. So we think that this may be one of the reasons we're we're seeking out researchers right now at Cure Alzheimer's Fund to start investigating that link. It's very new. Head injury is a risk factor, stroke, even loneliness and emotional trauma, losing a loved one, going through a bad divorce, all have been shown to be risk factors for this disease. What do these have in common is that whether it's advanced age, family history of genetics, gender and inflammation, head injury, stroke, which is an injury, emotional trauma, which can lead to cortisol in the brain, which kills neurons, insults to the brain that kill nerve cells can help trigger this disease. So, if you think about a football player who, 20 years after retiring comes down with dementia, some of the same pathology is involved there as well, or boxing. But I'll tell you the nuances of that, how it's a little different, but there's common pathology there with Alzheimer's disease. And the current drugs we have, Aricept and Namenda, are basically better than nothing, but not much. They don't treat the disease itself. They treat the symptoms. They help get the most out of the neurons and nerve cells that are still there, preserving neurotransmitters and neurochemicals, but neurons are still dying, the synapses are still being lost. Alzheimer's is still insidiously ripping apart that tapestry of memories and experiences encoded in your neural network. These drugs don't stop that. We have to preserve the neural network, stop that tapestry from being ripped apart. So, let's go ahead. Oh, now it's going to spin again. So where did this disease come from? This is Dr. Alzheimer here. This was his patient, August Dieter. And in 1906, he presented her case in Bavaria to an august group of psychiatrists, and including Carl Jung, who was actually in the audience. And he presented her case, and he suggested that he saw that when he found these certain lesions in her brain that I'll show you, for the first time, someone suggested that physical lesions in the brain might lead to a psychiatric illness. And it did not go over well, because to say that in 1906, that psychiatric illness was being caused by physical lesions in the brain, they looked at him like he had four heads. Even Carl Jung told me he was full of it. And it turned out he was right, that even today now, some of the most promising research in depression, schizophrenia, even autism, shows that inflammation in the brain physically is helping cause these diseases and are serving as some of our greatest targets now for therapeutics. And in Alzheimer's, I'll show you that that's similar. So this is from Alzheimer's Journal. He said he went into the room, he found this patient, 55 years old, sitting on a bed with a helpless expression, and he interviewed her. He said, "What is your name?" And she said, "August," which is correct. He said, "Last name?" And she said, "August" again, so obviously having problems. "What's your husband's name?" Again, she said, "August, I think." "How long have you been here?" And she said 3 weeks. She had been there actually 2 days. This is consistent, this loss of continuity of time. And then he said she broke down and cried and kept screaming to the doctor, "I've lost myself. I have lost myself." And that's what this disease is. It's losing oneself because it rips apart that neural network that is creating all of your memories and experiences that have defined your life. Most terrible thing that can happen to you, especially when you know it's happening in the beginning. The frustration, the agitation, the depression that comes along with that is just heartbreaking. So where does this happen? Well, see these two guys? This yellow part here is called the entorhinal cortex. This red thing is called the hippocampus. And this is the hippocampus side view over here. So I'm going to explain how this works. Every day, you're taking in sensory information. So what's happening is you're hearing things, you're using your senses, that information comes in, and you have to store it somewhere, at least temporarily, before it gets registered. So think about information coming in on a thumb drive, you put it in your computer, and then eventually you transfer it to your hard drive. Well, the hippocampus is like the thumb drive. It's the short-term memory. So in Alzheimer's disease, what's happening is that the connection that allows you to have short-term memory is going away. So as the sensory information comes in, right behind your forehead, deep in your brain back here, there are these areas that take the sensory information and they bundle it into one cable, so to speak. It's called the perforant pathway. So picture this big cable of wiring of nerves. That cable comes in and it perforates the hippocampus. And the hippocampus means seahorse in Greek because it looks like a seahorse. And so picture this guy being perforated at 90 degrees and your entorhinal cortex, your sensory information is coming in and saying, "Here, keep track of this. Keep track of this." So you're going to know what you heard or smelled or ate or felt 5 minutes ago or 3 minutes ago. That very connection where the sensory information has to go into the short-term memory area is slowly short-circuited. The pathology of the disease stops the information from flowing. So eventually, what will happen is that as you sever this, it leads to this loss of continuity of time. You can't keep track of what's going on. You're experiencing things, but first you can't remember what happened 5 minutes ago, 4 minutes ago, 3 minutes ago, even 10 seconds ago. And I said you can't remember, but I just misspoke, because this has nothing to do with remembering. What's happening here is there's no learning, right? Because if you're hearing me, and my words go from your sensory cortex for hearing to your hippocampus, and you can't store what words I just said, you're not forgetting what I said later. You never learned it. And this is just as much what goes on in Alzheimer's as memory. This is just as much a learning disease as it is a memory disease. So what will eventually happen is that you lose your sense of self, because sense of self requires integrating and associating new information in the context of space and time. What that means is that as you learn new things, learning is based on associating new information with what you already knew. You make new synapses that connect with your old synapses, because you never just learn something new in a vacuum. From when you're in the womb, you're associating what you learned with what you already knew. You can't do that anymore as Alzheimer's progresses. You can't put things in context. You can't store them. It's short-circuited. So eventually, late-stage patients are living in the moment. Sensory information is coming in. There's no context of what they've already known. There's no perseveration or thought about it. It's sensing information in the moment, but that sounds good if you're into meditation, right? It's great to be living in the moment. But if there's no self-awareness, if there's no longer a self there to know and enjoy the bliss that can come with living in the moment, it can be terrifying, frustrating, and agitating instead. So I like to use this. This is a table that came out. I wrote a book with Deepak Chopra named Superbrain, and Deepak and I just spoke actually last night in Amsterdam. I just flew in from Amsterdam to do this, so I'm a little foggy. I hope you don't mind, but not that I did that in Amsterdam, but I did go to the U.S.-Netherlands soccer game, and that was scary. And that's where we won. We came back from 3-1 to beat the number 6 team in the world, Netherlands. And I was very careful about cheering amongst 100,000 people wearing orange T-shirts. And I very much needed this part of my brain, the brain stem. Fight or flight, basic survival, no need for acquired memory, just knowing exactly what to do when things get rough, okay? So the brain stem is 400 million years old, and this is not touched in Alzheimer's disease, okay? That's left alone. There's no acquired memory here. In other words, you're not learning, this is just genetic memory, innate. We call it they call it the 4 Fs, but it's fight or flight, feeding, and reproduction. And so then you have the limbic system. You are a tough crowd. Then you have the limbic system, which is 100 million years old. And this is where the first memory comes. And the first memories we had were actually, this is evolutionarily, were memories of pain and pleasure. Because when you remember something that's painful and anticipate it in the future, that creates fear. And that's a survival mechanism. When you remember something that was pleasurable, that creates desire as you anticipate it in the future. And that also, both of these are driving reproduction together with the innate instinctive brain here. And then only 4 million years ago, the neocortex, all this stuff up here, came about. This is the intellectual self, but this is also the self that has meaning, purpose, identity, creativity, and self-awareness. It's where you're moving away from just pure selfishness, I want to survive. And as the brain's evolving, we're going more toward a vector of self-awareness, where instead of just surviving, we want to thrive. From survive to thrive. We want to do more. We want to be creative, productive. Mozart, Galileo, Martin Luther King, make the world a better place. That comes out of the neocortex. And in Alzheimer's disease, so our brain's on a great vector. This is only 4 million years old. This one's 400 million. Believe me, this one has its way, okay, seniority. So at any given moment, what we wrote about in Superbrain is that your brain stem and your limbic system are trying to rule you. So we tell people, keep track of where you are. Ask yourself once in a while, am I in my brain stem, am I in my limbic system, or am I in my frontal cortex? It really helps to stay out of trouble and to be more creative. So anyway, okay, I won't go near that again. So anyway, Alzheimer's begins here in the limbic system and spreads out to the neocortex over time. And what actually happens is you have this pathology, these plaques, this big gunky globs that accumulate outside the nerve cells, and inside the nerve cells you have what are called tangles that choke the nerve cells and make them die from within. So these are the pathologies that Alzheimer described in that patient back in 1906, and he said, this causes the disease. And now we know that there's a third pillar. Besides plaques and tangles, there's inflammation as well. So these are healthy neurons, and these are the plaques. And then what happens is the pathology starts here in the short-term memory area, and then slowly makes its way from the back to the front to the frontal cortex area. So you might ask, how does pathology spread? Looks like a fire, right? Even though it's blue, looks like a fire has started in the brain and it's spreading. The reason is these guys, these tangles that are made up of this protein called tau, they're like these twisted pretzel-like things that form inside the cell body and out in the processes. They spread. This is new information just over the last 5 years. A dying nerve cell with tangles spits out the tangle goes to a healthy nerve cell and makes it sick. So tangles are like a fire in the brain that keeps spreading. So when these poor guys who have played football or boxed get demented 20 years later, it's because they got a bunch of tangles in different spots of their brain with punches to the head or with concussions or helmet-to-helmet hits, or could be a bomb blast in Iraq or Afghanistan. And then as those tangles spread to the brain for 10 or 20 years, eventually they decimate enough neurons that cause enough inflammation that dementia ensues. So the question that's been really haunting the field of Alzheimer's for 30 years is, what makes the tangles form in a person who's not playing football or on the battlefield or boxing? What makes those tangles form? And the hypothesis that has been the most popular for the last 30 years, and I helped start it way back when I was a student, is that the amyloid plaques start the tangles. But this has been highly controversial because it turns out when you make mice get Alzheimer's disease with human genes, they get plaques, but they don't get the tangles. And they say, well, why aren't they getting tangles? And many of us said, well, because it's a mouse. It's not a human. So the key was to do that a little better. Now I'm going to show you what we did. So let me just go through it. Here was what we knew. From 1906 to 1986, after Alzheimer's described the disease, 80 years. We knew plaques, tangles, and inflammation, but we had no idea what caused them. And then the first big break came in 1987 when I and others discovered the first Alzheimer's gene. I named it amyloid precursor protein because it's the protein that makes the amyloid. So here's the plaque, and here's this big core of amyloid in the middle, and it comes from a little protein that's snipped out of a bigger protein. So if you picture a piece of rope, and then in the middle you snip in two places and get a little segment out, and that little guy starts to accumulate in the brain, that's what makes the amyloid. So that's why we call it the amyloid precursor protein. Then we found these other genes in 1995 called the presenilins. They actually help make the snip of the rope. They're the scissors. And then at Duke University, we didn't find this, we found these three, but then this one was found at Duke, ApoE. This is a risk factor that increases risk for the disease, but mutations in these three genes guarantee onset, regardless of lifestyle, usually by 60 years old, many times 50 years old. We even, like I said earlier, we have families with these presenilin mutations here, where they get this disease in their 20s. They're rare, but they teach us the most about what's going on. In fact, now we know that Alzheimer's patient August Dieter actually had a mutation in presenilin 1. That's why she had such early onset disease. So what can we do with these genes? Well, genes teach us, like I said, what's going wrong. You find the mutations. This allows you to come up with targets for drugs and other therapies, and then you can do intervention. So a great example is heart disease. You know, long ago, there was a family that was being studied by two Nobel laureates. They got their Nobel Prize for this, Brown and Goldstein. And they found families that had early onset heart disease at 50, 40 years old. And what they noticed was they had a gene mutation that allowed them to make too much cholesterol. So for the first time, they suggested, based on a rare early onset form of heart disease, based on genetics, that high cholesterol was the issue. And now, of course, with diet, exercise, weight control, if necessary, statins like Lipitor, Crestor, we keep our cholesterol down, and incidence of heart disease has gone down. In Alzheimer's, the analogy is perfect. It's this little protein called amyloid beta protein, or A-beta. This is the little guy that's snipped out of the big protein, APP. So this was the first Alzheimer's gene. It's a protein that gave rise to this little guy, A-beta. And here's a diagram of it being made, and it's forming clumps. And here's the two things that happen. You can make the plaque, shown here, but also some of the little clumps that don't get into the plaque can go right here where you're trying to make a synapse. This nerve cell is trying to create a connection with that nerve cell as part of your neural network for learning and memory. And this stuff is like gunk that gets in there and short circuits it. It's almost like when you have an old stereo and you turn the volume knob and you get a ton of static, and you just get one of those dustbuster things or whatever, and you spray the volume knob and get the dust out, and the connection's good again. This is like the same thing. This stuff is actually interfering with the connection between these nerve cells, and then eventually you get a plaque. And the plaque can actually act as a reservoir of more of this crap that basically prevents nerve cells from communicating. And this is the problem in the disease. But again, there was still a question of whether the amyloid was really causing the disease. You have to still understand it's the tangles that spread that kill the nerve cells. So is amyloid and tangles connected? We didn't know. So in the meantime, many different companies did studies where they, if you think about the brain full of amyloid like a sink overflowing with water, right? You try to either turn off the spigot or unclog the drain. So many companies tried drugs to lower the amyloid production in the brain. Others tried to clear the amyloid out of the brain. Some of these drugs just weren't very good. They weren't potent, or they were toxic, or they didn't get into the brain. But some of them were decent, and still every trial failed. So again, you had the Wall Street Journal, the New York Times, people coming out saying, Tansey and all those guys are full of it. Look, we targeted the amyloid, and it's still not helping the disease. Amyloid must be the wrong target. Even though all the genetics so far says it's amyloid, why are these trials not working? And so then we learned this. This was probably one of the biggest studies that came out. This was from an Australian study where they were looking at amyloid in the brain. You could actually image and start to see the amyloid and plaques in the brain. And when they did this, what they noticed was something profound. The amyloid starts accumulating in the brain 15, now probably even more, based on a new study that came out this past week, 15 to 25 years before symptoms, amyloid's accumulating in the brain, okay? And then this is shown here too. So this is amyloid. This is busy slab. Follow this red curve. This is amyloid going up, accumulating in the brain. Alzheimer's begins here. Then, see how this plateaus? We know from the new studies that just came out this week, it actually starts to go back down, like this. They don't even plateau. So think about what we were doing. We were treating patients for amyloid out here, and the amyloid was building up over here. In other words, it was too late. This is like having a patient go to a cardiologist with congestive heart failure, had a heart attack, and the cardiologist says, oh, here, simple, just take this little pill for cholesterol, just take a Lipitor. It's not going to help you if you're not going to stop congestive heart failure or fix your heart after a heart attack. You had to take that Lipitor and start managing your cholesterol 25 years before, so you didn't get that far. Same exact thing here. You have to hit amyloid 15 to 20, maybe 25 years before the symptoms. Now we know that. So now what we're seeing is new drugs like beta secretase inhibitors, as they're called. There's these two scissors to snip the rope to make the A-beta peptide. Beta secretase is one. We're seeing inhibitors for those in trials. Cure Alzheimer's Fund, together with us and UCSD, are coming up with modulators to stop the other scissors, the gamma secretase. We also see antibodies. Biogen just had an antibody that, for the first time, they could show when they lowered amyloid, they improved cognition, and they used patients who were very, very early in the disease, learning from that graph I just showed you before this. So now, the new amyloid trials are being done with patients who are very early in the disease, or even people who don't have the disease yet, but they have, by imaging, a lot of amyloid in their brain, so they're at highest risk, and you track them for 2 or 3 years and see if treatment will stop them from converting to Alzheimer's despite the amyloid in the brain. So now we're doing it the right way. Another drug is PBT2, which I developed with a company I started called Prana Biotechnology. This also gets the amyloid out of the brain. We have that in trials. So now we have better trials where the mantra is right patient, right drug, as the president said for his precision medicine. He announced a precision medicine program in his State of the Union address. But it's not just right patient, right drug. It's right patient, right drug, right time. All right? Preventative medicine is you have to use the right drug at the right time, just as much as having the right patient. So now this is where we're at. So we have the plaques. They deposit. These tangles form inside the neurons. Here's the plaque, and start to kill the neurons. The tangles spread like a fire through the brain. And then neuroinflammation comes in. This is the brain reacting to all this damage. And actually, neuroinflammation, even though it's well-intended, kills many more nerve cells than the actual original pathology. And then it spreads through the brain like this. But still, there was a big question. Does amyloid cause the tangles? And the problem is that in mouse models, the answer was no. Mice didn't do it. They put the amyloid in with the Alzheimer's genes. They didn't get the tangles. So we created something that the New York Times dubbed Alzheimer's in a dish. And this was, this guy's idea, Duyan Kim and my group, who came up with it. And it's based on stem cells. So you take human stem cells, like for example from skin, and then you can turn those into human neurons like they are in the brain. And originally we were growing them in Petri dishes in liquid, right? So here are the cells, and then this is the amyloid being made. It floats around in a dish. you don't get pathology, right? And Dooyan Kim had a very simple but astute observation when he said, the brain's not made of liquid. Why would we try to model a disease in a petri dish of liquid? The brain is made of gel, okay? If you didn't have a skull around your brain, it would be like 3 pounds of Jell-O quivering in a dish, okay? So we said, let's do this in Jell-O. Well, not really Jell-O, but we were using a gel matrix, a 3D matrix, and sure enough, when you grow the neurons in gel and you allow them to actually space themselves out, make connections in the gel, form neural networks, now you don't just get the free-floating amyloid in the liquid, it starts to form plaques in the actual gel. You start to recapitulate the amyloid plaques in a 3D matrix in 6 weeks. Just 6 weeks, you get plaques. What takes 6 decades, 7 decades in human, you're getting in 6 weeks in the dish. And this just shows you where this orange thing in the middle is the plaque. These are all the nerve cells. If you showed this to a neuropathologist, they might think you're looking inside of a mouse brain. This is actually human neurons with a real plaque, and we're imaging through the plaque down the z-axis. So we're looking from the top to the bottom of the plaque. And the most amazing thing is as you're getting these plaques, you just wait 2 more weeks, and you get the tangles. So plaques first, then the tangles form. This is a picture of a tangle from these 3D cultures right here. Then you can use treatments like our drug we're using, where this is untreated. We can see we block the plaques here with the drug. We can use those same drugs that block plaques, and here's untreated. All this brown stuff are tangles inside of nerve cells, but if you use drugs to stop the amyloid, either this one or this one, you don't get the tangles. So what this says is that tangles follow the amyloid in this system. If you stop the plaques, you stop the amyloid, then you'll stop the tangles. So this was the first proof, and that's why this paper made such a big splash in the field, because it finally settled a 30-year raging debate. Is it amyloid or the tangles? It's both. It's both. But in Alzheimer's disease, amyloid causes the tangles. If you're playing NFL football and you were too unfortunate to have too many helmet-to-helmet hits, you don't need amyloid to get tangles. If you're on the battlefield with one bomb blast and the bobblehead effect, where the brain shakes violently, you can get tangles instantly. So you don't have to have amyloid to get tangles. But if it's Alzheimer's disease, you have tangles that are killing nerve cells because amyloid caused those tangles. That's what we learned from these experiments. Tangles mediate the original cell death. That's the fire. Amyloid is lighting the match. Inflammation is then fanning the flames. That's what we've learned. This is new information, folks. What you're hearing right now, is about as new as you can possibly get in terms of the synthesis of what we learned from these different genes and models of Alzheimer's disease. So we finally have some idea of what's going on without having to fight with each other about whose pathology is more important. I'll say it one more time. Tangles cause the cell death. They spread like a fire. In the case of Alzheimer's, amyloid starts it, but there are other ways to get tangles. So that's what we have. We also figured out some of the ways that amyloid can lead to tangles, some of the requirements. I won't get into that. So if you're going to treat this disease and do the right timeline, amyloid buildup is very, very early. You have to hit way early on. Then amyloid starts to cause both neuroinflammation and tangles and cell death. This causes more neuroinflammation. And neuroinflammation acts as yet another insult to the brain because you have free radicals and oxidative stress killing more nerve cells, and this comes around and causes more amyloid and tangles. So you get this vicious cycle that goes around and around. That's what we now know. So in terms of treating the disease, you want to hit all 3 of these. You want to hit the amyloid early, you want to hit the tangles, and you want to hit the inflammation. And I would say that if a patient has full-blown Alzheimer's right now, you want to hit inflammation, but you also want to hit these as well. So we're going to need a cocktail. So what we've done is we've made 3-dimensional models of Alzheimer's. This one's for plaques and tangles. We have a new one that covers the inflammation. This one covers how stroke leads to Alzheimer's. This one covers how the tangles spread from dying nerve cells to live nerve cells. We're putting this all in one big 3D model and using nanotechnology to deliver the drugs to this system. So modeling the entire Alzheimer's brain in a dish. Why? Because mice don't work. Mice are not humans. Mouse models have failed us. They don't recapitulate the full disease. You can only do parts of the disease in mice. Tangles in this one, amyloid in this one, inflammation in that one. But this does it all together. So this is a Cure Alzheimer's Fund initiative. We're using what's called the Alzheimer's Genome Project to come up with all the different genes and mutations that we need to incorporate into the system. We now have 3,200 whole genome sequences for Alzheimer's disease in our data bank, which is huge. And these are some of the genes we found. I can't go through all of them, but these are just piles of genes that affect amyloid. These affect the tangles, a huge growing number of genes affecting inflammation in the brain. And one in particular, CD33, is now teaching us how to stop the inflammation. And then we have to leave soon to go get that family picture thing and dance to Sister Sledge. So I'm going to try to wrap up because it's already 3:34, so I'm paying attention to time. But what I'll tell you is that the microglial cells, these guys, these are the housekeepers in the brain. They're like helping the neurons out. They clean up, they feed. But as soon as they see a bunch of nerve cells dying, they assume it's an infection. Okay, they assume that nerve cells are being attacked by bacteria or viruses or fungus, and they become a psycho SWAT team and start shooting out free radical bullets to kill what they believe to be an invader in the brain, killing these neurons. That's how the brain's very primitive immune system works. It's not like the rest of the body. It's like at the same level as an oyster or a horseshoe crab. So what we discovered from genetics that came out of the Cure Alzheimer's Fund Genome Project was this is the switch. CD33 is on the surface of these cells. If we can turn off CD33, and we're trying many different therapies to do that now, if we can turn off CD33 on the cell surface, you can keep these microglial cells chilled out. So I'm calling this the quest for the microglial chill pill. Why? We have recently 30 brains of people who died in the 80s, no cognitive problems. You look in their brains, full of plaques and tangles. Plaques and tangles clearly at the Alzheimer's level. No dementia at 80. What did they all have in common? They didn't have this, no inflammation. So these were genetically protected people. It turns out you can have a head full of plaque and tangle that defines this disease, as Alzheimer's first showed, but if there's no inflammation, you don't get demented. Because this inflammation, like the plaques and tangles kind of push you up the cliff, inflammation throws you off. So if we can chill out microglial cells using these targets, as I showed here, and you can have a lot of plaques and tangles and survive and not necessarily have this disease. This is a big initiative now, trying to find molecules that block this key triggering gene, CD33. So in the end, we're going to have a cocktail to hit amyloid, tangles, and neuroinflammation. Cure Alzheimer's Fund is leading the way on this. But meanwhile, some of the things you can do to help reduce risk based on different studies. Physical exercise is very important. If you have a little thing that measures your steps, probably 10,000 steps per day. Mediterranean diet, less red meat, more fruits, nuts, veggies. Socially engaged. These are some of the Ayurvedic herbs we've tested, ashwagandha, also cat's claw from Peru. They seem to do, this one helps get plaques out of the brain, as we've seen. This one helps break up tangles. Learn new things. So what you're doing right now, you're protecting yourself. If you're doing Lumosity or crossword puzzles, not so much. Okay? It's not about doing games. Brain games are fun, but if you want to protect your brain, you need synaptic reserve. As you head toward retirement, you want financial reserve and synaptic reserve. Why? Because when you learn new things, you make new synapses, you strengthen the ones you have, and basically the degree of dementia in Alzheimer's correlates with loss of synapses. So the more synapses you have, the more synapses you make, the more you can lose before you lose it. So build them up, keep learning stuff, just like you're doing here. Emotional stress, we have a paper going out on meditation, which is low. It looks like meditation in the study we did is helping get amyloid out of the brain, and also reducing inflammation. That's being submitted to New England Journal of Medicine over the next week or so. And sleep. It's during sleep that much of your long-term memory is consolidated from short-term memory. It's when you take stuff off that hippocampal thumb drive onto the hard drive, the frontal cortex. And you also, it's during sleep. Now we've just learned over the last week, the brain has a lymphatic system. Who knew? I mean, this has rocked the world, that we never thought the brain had a lymphatic system connected to the rest of the body. And some very clever postdoc discovered there is actually a lymphatic drainage out of the brain. And that combined with other data suggesting during deep sleep, this is what I call mental floss, you're clearing a lot of this crap like amyloid out of your brain. To get deep sleep, you have to make sure that preferably get 7 or 8 hours. You might get it with 6, you probably won't get it with 5, just so you know. So sleep is very important, much more important than we thought. So now, before we go outside, for those who want to stay, I'm also a musician, and I actually play keyboards on the side with Joe Perry of Aerosmith, and I played organ on the last Aerosmith album. It's just something I've always done on the side. But besides rock, I like writing ballads, and I wrote a ballad with Chris Mann, who is a crossover opera and pop singer. He made it on The Voice as a finalist, and he had a #1 adult contemporary album. He's been affected with Alzheimer's in his own family, so we wrote together last summer this song we call Remember Me, which is meant to be I would say, an anthem giving a voice to Alzheimer's patients. And if I can figure out how to do this, I'm going to bring up the YouTube because they also did a video around this, the Cure Alzheimer's Fund supported. I want you to hear it. So let's hope this works.
I need someone to hold on for me, to what I can't seem to hold on to. The life we used to live is slipping through my fingertips like a thread that's unraveling. I suppose that nothing lasts forever, and everything is lost in its time. When I can't find the words that I'm trying to speak, when I don't know the face in the mirror I see, when I feel I'm forgotten and lost in this world, remember me. Remember me. I know there'll come a day when I have gone away and the memory of me will fade. But darling, think of me and who I used to be, and I'll be right there with you again. I hope I'm one thing worth not forgetting. Tell me that you'll never let me go. When I can't find the words that I'm trying to speak, when I don't know the face in the mirror I see, when I feel I'm forgotten and lost in this world, won't you please remember me? I hope I'm one thing worth not forgetting. Tell me that you'll never let me go. When I can't find the words that I'm trying to speak, when I don't know the face in the mirror I see, when I feel like I'm lost and alone in this world, won't you please remember me?
So in ending, I'd like to thank you for being here, and just know that we won't give up until we stop this disease. Thank you very much.